Welcome to MarkScheme, the wave model. Everything you need, made visual. Drop a stone in a still pond, and the ripple races outward, across the whole surface. It clearly travels. So here's the deceptively simple question. This whole topic answers. When a wave crosses the water, does the water itself travel along with it? Watch the gold marker. As the pulse passes, that one bit of water lifts up, then drops back down, and it ends up exactly where it started. The shape moved right across. The water did not go anywhere. A wave carries energy forward, while the medium just oscillates in place. Hold on to that. It is the single most important idea in the whole of waves. Here's exactly what this covers, straight from your syllabus. IB Physics. Theme C, Subtopic 2. The two kinds of wave, transverse and longitudinal, plus wavefronts and rays. The big idea that a wave moves energy, not matter. Every wave quantity, wavelength, frequency, period, amplitude, and speed. The two equations that tie them together. The two displacement graphs students always confuse. The electromagnetic spectrum, and sound as a longitudinal wave. And here's the good news, and it's a big one. Every single part of C.2 is standard and higher level common core. There is no higher level only content here at all. All of it is on both the SL and the HL papers. So this one video serves both. No prior physics is assumed either. If you know that things can wobble back and forth, you're ready. Let's make that idea undeniable. Here is a proper traveling wave. A whole row of particles, each joined to its neighbors. I'll set it moving. The blue shape sweeps steadily to the right, and it is genuinely carrying energy along the row. But now, lock your eyes on the gold particle and its dashed track. As wave after wave goes past, that particle just travels straight, up and down, its own little line. It never drifts to the right, never follows the wave along. Every particle is doing the same, oscillating in place. The wave propagates. The matter merely oscillates. Energy is transferred with no net transfer of matter. That sentence is worth marks. Learn it word for word. Waves come in exactly two flavors, and the difference is simply the direction. The particles wobble compared with the direction the wave travels. In a transverse wave, like the one we just watched, or light, or a wave on a string, the particles oscillate at right angles to the direction the wave moves, up and down, while the wave goes sideways. In a longitudinal wave, the particles oscillate. Along the same line, the wave travels, back and forth, left and right. Watch what that does. As they slosh, they crowd together into dense regions, called compressions, and spread apart into thin regions called rarefactions. And those compressions march steadily along the row. Same deal though. Keep your eye on the gold particle. It only jiggles about its home spot. It doesn't travel with the wave. Sound is exactly this kind of wave. One more piece of language. When we draw waves spreading out, we use two tools. A wavefront is a line joining all the points that are in step. Say, every point sitting on a crest at the same moment. From a point source, they're circles, getting bigger. A ray is just an arrow pointing the way the wave travels. And here's the neat rule. A ray is always perpendicular to the wavefronts. Wavefronts show the shape. Rays show the direction. Now let's name what we can measure. Wavelength, the Greek letter lambda, is the length of one complete wave, most easily read from one crest to the very next crest, measured in meters. Amplitude, A, is how far a particle moves from its rest position to a crest. The height of the wave, also in meters. And be careful. Amplitude is not the wavelength. One is a height, the other is the length along the wave. The next three are about timing. The period, T, is the time for one full oscillation, one complete cycle, in seconds. The frequency, F, is the flip side. How many complete cycles happen each second, measured in hertz. And the wave speed, V, is simply how fast a crest travels across the medium, in meters per second. 5 quantities, 3 lengths and timings, and 1 speed. And 2 little equations lock them all together. Let's build those next. Here's where it all clicks together, and it's worth deriving, rather than just quoting. First, frequency and period are 2 views of the same thing. F equals 1 over t. If one cycle takes 1/5 of a second, you get 5 cycles a second, 5 hertz. Now for the speed. In exactly 1 period, t, the wave moves forward by exactly 1 wavelength, lambda. Speed is distance over time, so v equals lambda over t. And since 1 over t is just f, that becomes v equals f lambda. Both of these are printed in your data booklet. Let's see v equals f, lambda breathe. I'm fixing the speed at 2 meters per second. That's set by the medium and won't change. Now I slowly crank the frequency up, because v is pinned and equals f times lambda. If f rises, then lambda must fall to compensate. Watch the waves squeeze together. Higher frequency, shorter wavelength. The two are locked in a seesaw at constant speed. Notice v equals fs, times lambda holds at every instant. As f doubles, lambda halves. Now the single biggest trap in this topic. There are 2 graphs that look almost identical. Both are a displacement on the vertical axis. Both are a lovely sine curve. But their horizontal axes are completely different. And reading the wrong one throws your whole answer out. On the left, displacement against distance. This is a photograph of the wave frozen at one instant, spread out through space. The gap between crests here is a length. So this graph gives you the wavelength. On the right, displacement against time. This follows one single particle as the seconds tick by. The gap between crests here is a time. So this graph gives you the period. And from the period, you get the frequency, 1 over t. Say it to yourself. Distance graph, wavelength, time graph, period. Different axis, different quantity. Model them, and you'll call a time a length. An instant loss of marks. Light is just one member of a huge family called the electromagnetic spectrum. All transverse waves, and here's the beautiful part. All traveling at the very same speed in a vacuum. See, 3 times 10 to the 8 meters per second. What separates them is only their wavelength and frequency, in order from long wavelength and low frequency to short and high. Radio waves, microwaves, infrared, the thin band of visible light, ultraviolet, X-rays, and gamma rays. Same speed, wildly different wavelengths, and v equals f lambda ties them all together. Sound, by contrast, is the classic longitudinal wave, traveling compressions and rarefactions of the air, exactly like the marching pattern we built earlier. And because it needs particles to squeeze and stretch, sound cannot travel through a vacuum. No air, no sound. Light can cross empty space. Sound cannot. Keep those two straight. Time to use it. Example 1. The cleanest possible V equals f-lambda. All my own numbers. A wave has a frequency of 50 Hz and a wavelength of 0.68 meters. Find its speed. Quote the equation from the data booklet. V equals f-lambda. Substitute straight in. 50 times 0.68. That gives 34. And the units? A frequency in Hertz times a wavelength in meters gives meters per second. So the wave travels at 34 meters per second. Always quote the equation. Substitute, then finish with the unit. Example 2 puts the two graphs to work. And this is where students bleed marks. On the left is displacement against distance. So the gap between crests is a wavelength. I read it as 0.40 meters. On the right is displacement against time. So the gap between crests is a period. I read it as 0.020 seconds. Two different graphs, two different quantities. Now combine them. Frequency is 1 over the period. 1 over 0.020, which is 50 Hz. Then the wave speed is f-lambda. 50 times 0.40, giving 20 meters per second. Notice you needed both graphs. The distance one for the wavelength, the time one for the period. That's the whole point of the pair. Example 3. Lives on the electromagnetic spectrum. Green light has a wavelength of 500 nanometers. Find its frequency using the speed of light. First, the prefix trap. Nano means 10 to the minus 9. So 500 nanometers is 5.0 times 10 to the minus 7 meters. Get that conversion right. And the rest is easy. Rearrange. V equals f-lambda for an EM wave, where the speed is SUS, to get f equals c over lambda. 3 times 10 to the 8 divided by 5 times 10 to the minus 7 is 6 times 10 to the 14 Hertz. 600 trillion cycles a second. And placing it in the family. Green sits right in the middle of the thin visible band. Above radio, microwave, and infrared. Below ultraviolet, X-rays, and gamma. Higher frequency always means shorter wavelength. Example 4 is the tough multi-stepper, and it mixes distance time with V equals f-lambda. A ship fires a sonar pulse straight down. The echo bounces off the seabed and comes back 0.80 seconds later. Sound travels at 1500 meters per second in water, at a frequency of 2000 Hz. The catch you must spot. In that 0.8 seconds, the sound goes down and back up. It covers twice the depth. So the total path is speed times time. 1500 times 0.8, 1200 meters. Have it for the one-way depth, 600 meters. Next, the wavelength from V equals f-lambda rearranged. 1500 over 2000 is 0.75 meters. And for a satisfying finish, how many of those waves stack up in the depth? 600 divided by 0.75. Exactly 800 wavelengths. One problem? Every idea from this video pulling together. Now the exam craft that separates the grades. 1. The golden rule of this topic. A distance graph gives you wavelength. A time graph gives you period. So before you read anything off, check what the horizontal axis actually says. 2. V equals f-lambda is your workhorse. But if you're handed a period instead of a frequency, Do f equals 1 over t first, then feed it in. 3. Unit prefixes are where careless marks vanish. Nanometers are 10 to the minus 9 meters. Kilohertz and megahertz are thousands and millions of hertz. So convert to plain meters and hertz before you substitute. 4. Every electromagnetic wave travels at c in a vacuum. So use f equals c over lambda. And with echoes, remember, the wave covers double the distance, there and back, so have it. And 5. Both equations are printed in your data booklet. Don't memorize, locate them. Quote, substitute, and finish with units. Finally, the 4 traps that quietly cost marks. 1. Confusing the two displacement graphs. The distance graph gives wavelength, the time graph gives period, and swapping them wrecks the answer. 2. Mixing up wavelength and amplitude. Wavelength is length along the wave. Amplitude is a height from the middle. Totally different measurements. 3. Forgetting f equals 1 over t. You'll often need the frequency before you can use v equals f lambda. And 4. The conceptual one examiners love to test. Thinking the particles travel along with the wave. They don't. They just oscillate in place. Only the energy moves along. Dodge these 4 and C2 becomes reliable marks. And that is C2, the wave model, fully covered. Transverse and longitudinal waves, wavefronts and rays. The crucial idea that a wave moves energy along, while the particles just oscillate in place. Every wave quantity, v equals f lambda, and f equals 1 over t. The 2 displacement graphs and how to tell them apart. The electromagnetic spectrum, and sound as a longitudinal wave. Every part of it sits on both the standard and higher level papers. Next in the course, we switch on the charge, current, and circuits. For more, that's markscheme.app. See you there.